Good day, good evening, Year 12 physics students. Let's kick this one off with a little joke. It's a bit silly, but anyway. A photon checks into a hotel and he's asked if he needs any help with his luggage. He replies, "No, I'm travelling light." Okay, I know that was really bad, so let's just move on. The reflection of light, that's what we're going to talk about today. I'll probably do a series of videos on this. The first one, this one, will be essentially on plane mirrors, talking about plane mirrors and their properties. We'll cover the law of reflection, which is a very simple idea and very easy to remember. And we'll look at constructing diagrams, ray diagrams, as a means for locating the image of an object that's been reflected in a mirror. Okay, so let's kick it off with plane mirrors. So what is a plane mirror? Well, let's draw one. Okay, so here we go. Plane meaning straight, linear. Okay, so here's my plane mirror, and I'll give it a bit of depth, bit of dimension. So we'll say this side of the mirror is the non-reflective side. Okay, so what are the properties? What are the properties of plane mirrors? Okay, so let's try and list a few. So I think the first, probably main property of a plane mirror is that the image that is formed is always virtual. So the image is virtual. That is property number one. Okay. Property number two, and this is very simple, this idea as well. The distance to image relative to the mirror, right, is equal to the distance to the object relative to the mirror. Okay, so very simply what we're saying is that if we have an object, say here, then we find the image of that object will be somewhere around here. Okay, so we find that the distance from the object to the mirror is equal to the distance from the mirror to the image. And that's always true in a plane mirror, always. So this is a virtual image. What is a virtual image? A virtual image is essentially an image that cannot be projected on a screen. Okay, so there's only really two types of images that we're going to talk about. One is real, the other is virtual. So a real image is an image that can be projected onto a screen. So a simple example of a real image is looking at a projector, projecting a movie or a PowerPoint onto a screen. That image that's formed on the screen is a real image, okay? Because we can actually, it's there. With a virtual image, it seems real. It seems like when you look in the mirror, you see that person on the other side that is you. That's nowhere in physical space. It's sort of set back behind the mirror, and it's not a real thing. It's just a virtual thing. Okay, so there we go. So we've got virtual images, and we've got the distance to the image is equal to the distance to the object. I guess one other interesting property with plane mirrors is that we always find that the image is laterally reversed. So what does that mean? Laterally reversed just simply means that when you look in a mirror, your left side on your person, on the call yourself the object, so your right side becomes the left side of the image. Okay, so left becomes right, right becomes left, and that's really all it means. Okay, you know that when you sort of raise your right hand as you're looking in a mirror, it looks like the image is raising the left hand. The image raising the left hand. How about that? All right, so let's move on. So plane mirrors, properties, there we go. What's the law of reflection? So angle of incidence equals angle of reflection. So let's sketch something in here, I guess. So I could say this is an incoming ray of light from somewhere, from an object perhaps, and what we find is the reflected ray will come off like so. And if we throw a normal in here, so normal meaning a line at 90 degrees to the mirror at that point there where the incident ray hits, so we'll call this the incident ray, This is called the reflected ray. And so this angle in here, we'll call that I, that's the incident angle, and this angle here, we'll call it R, the reflected angle. Okay, so the basic law of reflection is angle of incidence. Sorry, I just realised that was off the screen. There it is. Law of reflection, the angle of incidence is equal to the angle of reflection. Okay, so that is the law of reflection. Okay, now it's true also for non-plane mirrors. If we have, I'll just give you a sort of a preview of what's coming up. If we have, say, a spherical mirror, something like this, which we could say is a convex mirror, this one. If we have, say, a ray coming in, ray of light hitting there, what we would find is that if we looked at the reflected ray, it would come off something like this. That's the incident ray. This is the reflected ray. Okay, sorry, I'll keep that straight. Gee, I'm good at these. Okay, that's the reflected ray, that's the incident ray. What we find is that the law of reflection is still true. I is equal to R, and here we still have a normal. Now the normal line is still at 90 degrees to the mirror, so we've got to think of, you know, this point on the mirror, even though it's curved, we can think at this point here, if we put a tangent in, so a tangent into the mirror at that point, then this line here is 90 degrees to that tangent. I know it doesn't look very accurate here, but that's the general idea. So we still have this law of reflection that applies to spherical mirrors, not just plane mirrors. Okay, and you know, we're assuming, of course, that it's a smooth mirror in both cases too, by the way. Okay, so we have that. So we have, coming back up here, we've looked at plane mirrors, their properties. We've defined the law of reflection. So obviously, a much easier way to state the law of reflection is just I is equal to R, as long as we know what I and R are. Okay, so let me just come back here for a second, and let's put normal in there, and this is obviously our plane mirror. Okay, good. All right. Okay, next thing, let's now look at ray diagrams. So what we could start with here is I'll just do an example. So ray diagrams, and we do ray diagrams for plane mirrors, but also for spherical mirrors. Okay, so here's the general idea, and you'll notice over here I said that for ray diagrams, the idea is that we're using triangulation. So and you'll see what that is as we put this together. So let's start with just a really simple object. So I'm just going to draw a little kind of triangle, I guess. Shade it in. Okay, so here's my triangle, and I'm going to place a mirror, say here, a plane mirror. So we'll call this the object. Okay, now we can sort of guess where the image is going to be, because given we know the properties, the image is virtual. It's, you know, the distance to the image is equal to the distance to the object, and we also know that it's going to, you know, the image is going to be laterally reversed. We can probably just guesstimate and say, okay, well, we expect the image to be here somewhere. But let's go through the process of triangulation just to verify that that indeed is the case. Okay, so how do we do triangulation? All right, so I've deliberately used a triangle here because it has 3 vertices. Okay, now we're just going to start with one, and you know, the way to really plot the image of this triangle over here, the image that's formed in that plane mirror, is to construct rays running from each of those vertices. Okay, so we'll start with one. And I'll just, you know, and it doesn't matter what direction you shoot it off at. So I'm just going to take a ray coming off, say, at this angle here. Tell you what, I'll use a different color. So if we have this ray coming off here, okay, and then we'll have another one, say, coming down through here. Okay, now given that we know the law of reflection, then we can construct our normals. All right, so we're saying this is an incoming ray from this point. So just imagine, you know, it's light coming off that object and reflecting off that object into the mirror, right? So 2 rays, and we could do an infinite number of rays because in reality that's what's happening. You know, light is everywhere. So we're just focusing on 2 rays. So we have this ray coming here. It will reflect sort of like that, yeah, where I is equal to R. In a similar way here, we'll have a ray that's reflecting off on this angle, say up here, I is equal to R as well, okay? So, what do we do with that? Well, this is where the idea of a virtual image really kicks in, because what we're going to do is we're going to pretend that these rays that are reflecting are actually coming from behind the mirror. So if we kind of project back, right, with these reflected rays, right, so sort of back in that direction, let's see how accurate my diagram is. I'm sort of in an awkward position here trying to draw this, so I'll do my best. Okay, so somewhere around there. Okay, so from the perspective of being on this side of the mirror and observing that image, or if you're the object observing your image in the mirror, this point, right, this point on the object has a virtual image right there. Okay, and so it's as if light is coming from that point and heading out in those directions. Because what you really see, you really just see the mirror, okay, the face of the mirror. But you know, because there's rays coming off at these angles, it appears as though there's actually something behind the mirror, whereas really it's not. So what you're seeing is coming from here and here. So that's one point. Let's do a similar thing for the other one. I'll go back to my black pen so the diagram doesn't get too messed up. So I'll shoot a ray from this point. I won't do it for all 3. I'll just do it for these 2. So if I shoot a ray off at this point, say something like that, and then another one, say down here like that. Put in our normals, something like this, something like this. The reflecting rays coming off like this. And this one will be coming up somewhere through there. So that's a reflected ray, that's the incident ray, reflected ray. Project those back. Well, this could be tricky. I'm going to cheat a bit here because I'm going to sort of know that I should end up at this point, okay, somewhere around there. So this ray is coming back through there, and then this one, somewhere like that, okay? So it's a bit bodgy, but whatever. Okay, so there is my other vertex of the triangle here. So we can sort of just start to put it together now, and you could see we could do a similar thing with that 3rd point. But really what it comes down to is, you know, we pick a point. Okay, I'll just quickly summarize that here. Let's just move this across a bit. So here's a mirror. We pick a point, right? We throw a ray out this way and a ray out this way. So we just need 2 rays, okay? We look at how they would reflect in that plane mirror, obeying the law of reflection, I is equal to R, and then we sort of pretend that these rays are really coming from behind the mirror, so we project them back, and then where they intersect is our image. So that's the object, and that's the image. This is our plane mirror, and that's basically a ray diagram right there using triangulation. Okay, good. All right, let's do maybe a couple of examples. How are we going for time? So it's about 30 minutes. Okay, I'll just do a couple of, I think I'll just do one example. This is kind of a fun question actually, so let me set it up for you here. So it's a good problem. It's a good thinking problem, okay? So the question really is this, what length mirror is needed for a person to be able to view their whole body. Okay, so what length mirror is needed for a person to view their whole body? Okay, so now a sort of a follow-on question from that could be, well, you know, where are you standing in relation to the mirror? Are you close to it or are you far away? Does that matter? Is that a factor? So does it matter where you stand in relation to the mirror? Relation to the mirror. Okay, so that's a good sort of follow-up question, and that's maybe something you could think about right now. In fact, you might decide to pause this here and then, you know, go try this out in a mirror. Just use your bathroom mirror, your bedroom mirror, whatever. See if you can actually see your whole person in that mirror, or even more than your whole person. Can you see above your head, below your head? Okay, so there you go. So maybe do that. What I'll do now though is I'll just set up the solution to the problem without giving it away. Okay, so I'm just going to draw a stick man. Okay, here we go. Better give him a smiley face. Make him kind of tall. Give him a bit of hair, I guess. So there he is. There's my stick man. Give him some hands. 3 fingers. There we go. All right. Now, the way to solve this problem. Okay, well, let's use numbers because it might be easier with numbers. So I'm going to say this stick guy is, I'm going to say he's like 2 meters tall because it's a nice, easy number to work with. He's quite a tall guy. Okay, so we're going to say his overall height is 2 meters. Okay. Now, given that, there I go again, working off the page. All right. You can leave feedback and give me advice on how to do this better. I'll get better at it. Anyway, here we go. So we've got this guy. He's 2 meters tall. What's the most important reference point in all of this? Well, it's really his eyes. Okay, because that's, you know, if you're looking at yourself in the mirror, it's your eyes that are taking in the light and forming the image in your brain, and so really we need to do it relative to his eyes. So let's look at, say, a lateral line across here. Oh, by the way, I just said the word lateral, which reminds me, let's come back to this for a sec, because one thing I wanted to mention here, which I didn't, was that we can see this property of images being laterally reversed. You can see that here, right? So you can see this image has been swapped around. Okay, the image is not like that, is it? Okay, so because it's inverted, if you like, that's basically what laterally reversed means. Okay, so back to this problem. Here we go. All right, so let's say the distance from his eyes or her eyes. Put a dress on her. Here we go. So it's a girl. Okay, apparently. Yeah, there we go. She's got short hair. Okay, a crop, kind of, cool, groovy sort of hair. Anyway, now, and maybe a piercing, something, yeah, it's kind of punk, knee tattoo, whatever. All right, so we've got the distance from her eyes to the top of her head. Let's say that's 30 centimeters. Okay, I know that's big. Oh, 20 centimeters. That's probably more realistic. And then the distance, sort of from her eyes to her feet to the ground, right? We'll say that's obviously, that has to be 180 centimeters. Good, great. Okay, so hopefully some people have figured out where this is going to go. But essentially, what we need to think about. So the mirror's over here somewhere, right? I'm not going to necessarily put it in, but the mirror's over here somewhere. If from her eyes, right, she wants to see the top of her head, then she needs the mirror to be 10 centimeters above her eyes. Okay, 10 centimeters above. So why is that? Why 10 centimeters? So I'm going to do that. I'm going to say, okay, well, this is going to be tricky. So that's going to be, the lateral line from her eyes to the mirror. So now the top of her head is obviously up here somewhere. Okay, so 10, so that's 20 centimetres. That line there is 20 centimetres. But the mirror only needs to be half that distance. Okay, so this is where the top of the mirror is. Why? Because if we draw a ray from her eyes to the top of the mirror, right, and we say the distance from that lateral line to the top of the mirror is 10 centimetres, 10 centimetres, that means the reflected ray, right, because of angle of incidence equals angle of reflection, law of reflection, we see that this ray will basically go to the top of her head. Okay, well actually I should do my arrows the other way. I should say this is the incoming ray. Yes, that's the incoming ray, and that's the reflected ray, which is, you know, incident to her eyes, so she can see the top of her head with that particular ray. Okay, so what does that mean? That means that this section of the mirror only needs to be 10 centimetres. Now you can probably figure out, you know, what length below that we need. So we just halved the 20 centimetres here to get 10. So obviously to see her feet, right, she's going to need a ray that's sort of, you know, hitting the mirror halfway between her eyes and her feet. So we know that distance there is 180, so halving that is 90. So we probably, I'm just going to guess and say that that would be somewhere around here. I'm saying, yeah, about there. So really the mirror only needs to be that large. Okay, here is the mirror. Okay, let's put our rays in. So we've got a ray that comes to her eyes from the bottom of the mirror, which is reflecting off the mirror from the ground, and, you know, angle of incidence equals angle of reflection. That's the incoming ray reflecting to her eyes. Same deal here. I'm trying to squeeze that in. That's I, that's R. So we find that this part of the mirror is half of 180, which is 90, right? So that's 90 cents. So the total length, the length required in this example, the length required is really just 1 meter or 100 centimeters, okay, which is half her height. So the answer to this question then, what length mirror is needed for a person to view their whole body? It's basically half the height, half your height, okay? If you want to see your full body as you're standing up in a mirror, then you need that mirror to be at least half your height. Good. And just to answer that second part, does it matter where? No, it doesn't matter where you stand. So we could draw a mirror, say further over here, put in some rays. We'd still get the same numbers here. Okay, good. Okay, that'll do for this one. Thank you.